Hi, this is Dr. Liu. In this video, we'll explain how the centripetal force works in these situations, such as driving a car. So on the left side, we have a car that's turning to its left. So we can assume that is actually on a circular path, or at least part of its path is circular. And the center of the circle is somewhere over here. So maybe here, let's just draw an arrow. So this is to the center of the circle. It's not exactly in our range. So it's turning left. That means it's actually going on this circular motion on the horizontal plane. And the free body diagram has already been drawn. We have the gravity here that is equal to mg. And we also have normal force because these two are the only two forces. This has to be equal to also mg to cancel the gravity. And there's also friction toward the center. This is the static friction between the tires and the road. So the static friction now is acting as a centripetal force pointing toward the center. So something that's interesting, static friction is acting as a centripetal force. So what if the road condition were to change, such as raining or snowing or even ice forming on the road? Then static friction will actually have a smaller maximum, and trying to make a turn at a sufficient speed may result in skidding, right? So that is unbanked road. What if you have the road banked just like this? You're still turning left, but you're on a banked road. There's a banking angle theta. So the difference is now the normal force points at an angle, right? It's because normal force has to be perpendicular to the surface. Gravity still is gravity, the same amount. And now if we look at these two forces alone, even without friction, let's just imagine even without friction, say the road is very slippery, can we still make the turn? The answer is we can still make the turn because here this normal force is pointing at an angle, and this is its vertical component. So this is normal force vertical component Ny, and this is its horizontal component Nx. Okay, so Ny balances gravity. So Ny, or N times the cosine of this banking angle, theta, is balancing gravity. And then the Nx, which is N times sine of this angle, because this is that opposite side of that angle, will be equal to the centripetal force. And in this case, without any friction, it will be able to sustain the motion to a certain extent. So this is the difference between having unbanked road and having banked road. And what about if you had friction? Well, this becomes more difficult. Let me give you an example. Say if you're driving really fast, and that means you may actually be sliding outward. So in this case, friction will be pointing this direction, right? Inward. Oh, that's not good. We need to change color. So friction needs to point inward in order to help pulling you in, because say your speed is too high, so you would require a larger amount of force, centripetal force. So friction will be pulling in. That would result in a horizontal component friction that helps normal force create that required amount of centripetal force. So what if you're slow, really relatively slow? So you'll have a chance of sliding in toward the center. So friction will actually point this way if that's going to happen. So friction will have some component pointing against normal force, so that the net force along the direction which is pointing toward the center, here the center this way, will actually be less because say you're driving at a less speed. Right, so this really depends on the situation. It could become difficult and hard to predict which way it is. You may have to make an assumption and see if the assumption works out. Say if you assume the friction is pointing toward the center, kind of down the slope and you found out that the force is negative, then it is not pointing toward this direction. You have to change your assumption. Okay, so another situation is this swing pendulum. So let's just imagine we have a pendulum. So this is vertical, and we have the string and the pendulum bob, and that swings in a circular pattern. Something that looks like this. So it doesn't really matter which way it swings, maybe this way, maybe the other way around, counterclockwise or clockwise as you look down at it. So it swings, and the question is how to analyze its situation. So let's just assume that this is a swing pendulum, and it has mass m, and has a radius, let's say length L, and it's either given a radius or an angle. And I think more common is to give an angle. So which angle it swings at. So this angle here. So the question is, so how fast is it swinging? So let's analyze this. V equals what? So we'll draw a free body diagram. We start from gravity. So this gravity here, Fg, or you can use the W sign, just like this W here. And then we also have this tension here, tension T. And there's nothing else. So where's the center of the rotation? It's right here, center of the circle, right? So per my trick, I want to point my axis towards the center. So the x-axis points toward the center. And I have tension, which has an x component, right? So this will be the tension x. This one here. Tension also has a y component. Tension y makes a box with the tension as a diagonal. Okay, so this tension y needs to balance gravity, so the pendulum bob doesn't rise or sink, and then this x component is responsible for the acceleration toward the center. So this x component is indeed the centripetal force. So I'll have tension y minus gravity equals 0. This turns into tension, this angle here, theta. So y is adjacent, so that is cosine theta equals mg. And from here we can find tension. Tension is equal to mg over cosine theta. Assuming we have all these quantities, we know the mass, we know the length of the string, we know the angle the string makes with the vertical, so then tension will be solvable, right? So this is in the y direction, right? And in the x direction, we have towards the center, so tx is mv squared over r, and tx is t sine theta in this case is mv squared over this r, which is that distance, is not L, right? So it's this distance. That will be L times sine of theta. So L sine theta. Right, so this r, this is distance r. Right. Okay. So now we have this. We already have solved for tension, right? So tension goes into this equation. So the left side becomes mg over cosine theta, and then times sine theta equals mv squared over L sine theta. looks like we're kind of running out of space. So let's repurpose our space. So friction here is centripetal force. We can move that over there. And now let's move the whole discussion toward the left. So now we can have it here. Okay, so now we have enough space to continue our derivation. Okay, so now we have this relation. This relation has m and m, so the m will divide out, and I will have, so I'll just draw some lines here saying that so now we move on to the right side to keep on solving. Oops, just said m is gone. G sine theta over cosine theta equals v squared over L sine theta. So now we're getting really close to finding v. So v squared is equal to GL, so sine theta times sine theta sine square of theta, and then cosine theta. So this velocity v is GL sine squared theta over cosine theta square root. So it seems that the velocity of this swing pendulum is independent of the mass. It is dependent on the length. So the longer this length is, well, the faster the velocity has to be, and also the angle. So this may be difficult to see it because there's angle on the numerator and denominator. So we can make some changes here. Sine theta over cosine theta is tangent theta. Then we'll still have a sine theta here left. So GL tangent theta, that is from sine over cosine. The sine square is square of sine theta, so we still have sine theta. The good thing of writing it this way is tangent and sine theta, they're both monotonically increasing as the angle increases from 0 to 90 degrees, and this angle is only defined between 0 and 90 degrees. So that means if you increase angle, this whole factor will increase. That means the velocity will increase. This tends to be consistent with my experience. If I swing something, the faster I swing, the higher it'll rise, right? It will just rise up, and then it will just drop down. Sometimes we can call this thing a clutch. If you have these structures that as you swing, they pop open. As you reduce speed, they start to close. Thank you.